Um, so, any questions from outside? We don't have any new people, I think so. Okay. So we're talking about basic logic, and as an example, I started with over here with algebra, and I mean not just even the algebra. High school algebra is even simpler because we are dealing with integers. Okay, but the point is to learn how to write proofs. Okay, and so even in this case, you have to be very careful, and there are certain standards that you have to follow if you want to write a proof that is really satisfactory. So that's an example. That's an example of a proof that is pretty much satisfactory. I don't want to go overboard with how much details you provide, but certainly one thing. So what you could add to this proof. Remember, we started with analysis over here, and in the analysis, I mentioned the definition. So you could, unless you follow that pattern over here, definition, theorem, proof, then the definition either precedes the theorem itself. Otherwise, how do I say that it is? I cannot even state the theorem unless I already have my definition before it. So logically, you start with the definition, then you sort of define terms, and then you say something about them. Okay, so the definition precedes the theorem, but if not, maybe it precedes several pages earlier. So then what do? You certainly don't want to forget it. So you might want to include the definition inside of the proof, which is what I did not do, but it certainly would be justifiable. So once again, if I definition here, it is a possibility. It is a good standard to follow. Is define everything that's available. It is just to put it, but otherwise it's your judgment of how much detail you want to provide. And you could go the other way, and you can really compress this into pretty much one sentence. Do you want to try to take this proof and compress it to one sentence? So A and B are, so the statement itself is one over as long as the sum of two even numbers is even. Now, this is just a reasonably, 7 lines of proof. You could try to make it shorter. There's really no requirement whenever you write a proof. It's hardly ever somebody says, well, your proof is too long. It has too many details. It explains everything just too well, so let's make it shorter. So that's really not a problem, but you could certainly, as an exercise, to shorten it. So what can we shorten? Well, probably not the computation over there. That is the key, right? The key is that little computation. In fact, if you just if you want to explain to somebody the proof, all you have to write is this formula that goes from the bottom, and you just point your finger at the things that in fact you can maybe even do this. This is pretty much the essence of the proof, right? So even plus even, and the result you see it's even again, right? So as long as you know what even is, then this line would cover it. Okay. So similarly, even if it is by 3 or by a number that computation is in the center of the proof, it is the inside of the proof, but it doesn't mean that everything else is can be omitted, even though in a sense it's less important. But since we're learning how to write proofs, it is in fact the inside is often immediate, at least. That for the most part, those problems we're going to face. It is, in fact, the rest of it is that you need to learn how to do. Okay. Okay. So let's see. So and then we moved on once again with logic to statements that are slightly less mathematical, just for practice. and there are two ways to modify a statement with different results. Obviously, it is the converse, contrapositive, and the negative. Okay, converse, contrapositive, and negative, or negation. Okay, so the easiest one is in fact the negative, because I could make the negative of the original statement. I don't have to do this conversion we did last time. So every student in this room is an economics major. You have to convert it to if that statement before you can speak of converse and contrapositive. But the negative is simply the opposite. So, and also very important to understand what the negative means. It means that out of the universe of all possibilities, you take a statement, and then the negative will be everything else. Okay, so what's the negative? Looking at the original statement over here, how would you put it? So every student in this room is an economics major. How do you cover all the possible outcomes in the universe like this?
None of the students in the
What?
None of the students in the
Not, but what if there is one? And one is and one is not. That is a possibility, and you haven't covered. So like I said, we split the universe into two possibilities. One is right there at statement A, every student in this room is an economics major. We have to say the negative, which is pretty much the rest of the possibilities. So if you omit the possibility that one is and one is not an economics major, then you are not covering everything. So instead of none, what's the word we're going to use? Not. You can just take that statement. Well, in fact, here's an easy. Every student in this room is an advanced major. Okay, not. Okay, that's your negative. Okay. Or if you want to have proper grammar, you start with not every student in this room is an economics. So if we want to, at least, well, let's explore for a second what it means that for not every student to be an economics major, you can restate it. Well, how about let's restate it in the positive terms. So not is just too prominent. Can you make it a positive statement?
Every student in this room is some other major besides economics.
Yeah, it is a little bit awkward, but yes. Say it again. Not there is.
Every student in this room is some major besides economics.
Yeah, in this room is a major other than economics. It is totally valid, and it also suggests that we only have two statements that are equivalent. So this statement and the we want to produce is exactly the same thing, just put it in different words, and it might look different, and so sometimes with more complex statements, it might be hard to actually recognize right away that it is the same statement. And let me give you one more. There is a student in this room of major other than economics. Okay, so all of these statements are the same. Very cool. Okay, and you can certainly move stuff around. This is the most common way, most direct way of saying things. And there's in mathematics and elsewhere, it is either start with there is, or it starts with every, or any, or all. Any, all of these. So most of the statements start either with one of these words, such as, once again, any, all, every, each, all of these are words, once again, in the positive sense, if you want to have a positive statement, or alternatively, it starts with there is, there are, there exists, and so on. Okay, so that's another way to put a statement in a precise foundation. Okay, so that takes care of the negative. We certainly will keep talking about this. Let's go on and talk about the controversial contrapositive. Contrapositive is, in fact, the statement which is equivalent, once again, another equivalent way to put our statement, the original statement. So we're done with the negative, and now we're going to move to contrapositive, which is the equivalent statement of the original. Just it is put in a kind of almost what we did just here. So a statement that is put in the positive sense, and we kind of want to put the same statement with in the negative sense, if that were really applicable. So once again, the statement has to be equivalent, but not identical. Okay, so contrapositive. Before doing contrapositive, as I pointed out last time, you have to turn the statement into an if-then statement, which I did. So over here, the statement is: if the student is in this room, then he is an economics major. Okay, so then the contrapositive and converse are sort of different, do different things, but both of them reverse the error. Okay, so the converse is, let me write out the converse right away, and it says that a student is an economics major, then the arrow points the other way, then he is in this room. So what can you compare this statement to the original? So once again, this is my statement A in the new form, and then I have the converse, which is purely reversing whatever was the conjecture or hypothesis has become the conclusion, and vice versa. Okay, that's what I did. So it was this way. The original A statement: student is in this room, therefore he is an economic major. Okay, so that's one, and then the other. Since in this, if a student is an economics major, then he's in this room. So can you compare these two statements? Compare or contrast? Up to you. Well, I mean, if you want to compare, just think about real possibilities of examples of when one statement is satisfied or not, and then the other one. So if we start with A, so there are not too many choices for the original statement. Every student is an economics major, that's it. So we are limited to our rule. Here we examine every student, ask every student, and the student says that I am an economics major. That's statement A. Okay. What about the converse? Is it the same statement?
Limited to all economics majors?
What?
It's limited to all economics majors?
It is limited to all economics majors, but also is it really limited? Think about if there might be economics majors out there, and we're making a statement about them somehow saying that that person would have to be in this room. Okay, so the statement is definitely much stronger, and it is simply not. It's not the same statement. So you can imagine when the condition statement A is satisfied, while B is not. B, let's say this is B, and vice versa. Right, so student in this room. So you might have a bunch of economic students in this room, but there are also economic students outside. Okay, so that gives me A, but not B, because B says that we just put all the economic students in this room, and then that's it. That's what B says. So the conclusion is for now is that converse is not the same as the original statement. Okay, it certainly not, and one does not follow from the other either. So, as an example from geometry, let me give you an example of a converse from geometry. The Pythagorean theorem. What does it say? Try not to miss any of the conditions. Yeah? Pythagorean theorem?
A squared plus B squared equals C squared.
That's the punchline, that's the conclusion. Okay, so then you have to work your way back and say where these numbers come from. Okay, let's try it. So A squared plus B squared is equal to C squared. So that's the ending. Think about a joke you're telling, and you don't give a punchline, right? It's not going to be funny because people don't know what it's about. So you have to build it up. So every theorem is the same way. So see, so I'm not really trying to recover what that story is. So.
That would be a right triangle.
What? Okay, right triangle. So don't never forget about right triangle. That's commonly forgotten. What else?
And you have to have, well, I guess you don't have to have A.
No, you have to have AB. Now you have to explain what AB and C are.
It's the legs and hypotenuse. A is one leg, B is the other leg, and C is the hypotenuse.
A, B, C are sides. It's sides. And but there is one condition that it is specifically that C is the opposite of the right angle. So I intentionally put it in the form of a if-then statement. So if we have a triangle that is a right triangle, if A, B, C are the sides, A and C lies opposite to the right angle, then A squared plus B squared plus C squared, well, I'm sorry, A squared plus B squared is equal to C squared. Okay, so that's the original Pythagorean theorem. The converse is very easy to set up. Well, it's not actually that easy. Because if, okay, here it is. Let me put it in the proper form. Right. So we'll raise right here. Okay, so we have a triangle with, that is the setup. The original setup is this. So we have a triangle with sides ABC. Okay, so that's the setup. Now it is followed by if-then statement. We have C, a sides, one of the sides that lies opposite to the 90-degree angle. Then we conclude that A squared plus B squared is equal to C squared. Okay, so the inverse will be then backwards. If you have a triangle with sides ABC, okay, and then you have that equation satisfied A squared plus B squared is equal to C squared, does it mean that the triangle is right triangle? Yes or no? If you remember from geometry. So who thinks that the answer is yes? So the rest think it's no, or they just don't know. Okay, so it is a correct guess, and indeed, if you think about it, it is. So if the equation is not satisfied, it's not going to be a right triangle. Okay, so the example of the Pythagorean theorem is that it's not just the theorem is true, but its converse is true too. But it's easy to think of the examples, which we started with, when it's not the case. When the statement is true, it might be all filled with the economics majors, but its converse is not true anymore. So that's in mathematics happens all the time. It is in fact special. It is in fact, if you look at the bottom, it is in fact two theorems, and they have to be proven separately. You start with the one assumption, you prove the formula, or you start with the formula, you prove the assumption of prove the conclusion that it is a right triangle. Okay, so that is certainly to watch out for, and never assume that the converse is true. Okay, so it happens all the time. Or in calculus, say a function that is differentiable is continuous. If the function is differentiable, then it's continuous. The converse. The converse, if it is continuous, then it's differentiable. Okay, so comments? What? First statement, second statement. What?
Converse isn't true.
Converse isn't true, right? So because there are functions that are continuous but not differentiable. Okay. Okay, so now the contrapositive is the same statement, but put in a different form, in kind of a negative thing. So let me try to do it. We do reverse the arrow backwards, but we also negate both the assumption and and the conclusion. So he's not an economics major. Then what?
He is not in this room.
He is not in this room, right? Once again, just take a minute to convince yourself that these two statements are identical, or they equivalent. They cannot, if one is satisfied, then the other one, and vice versa. So if every student in this room is an economics major, then if we have somebody who is not an economics major, he cannot possibly be in this room. Okay, so that's the same statement. The point being, obviously, then if you can proceed to the proof, you got to prove something, and then to proceed to the proof, you can go directly, or maybe it's not quite obvious at first. Well, what is that? What to do? Then you look at you can modify the statement you're trying to prove. Well, one of them, well, there are two now. Either look at the negative or the contrapositive. If you prove the contrapositive, then you're done because it's the same statement. You have proved A. On the other hand, if you disprove the negative, then that also correct. Okay. Disprove the negative, probably not a good way to put it, so we'll get to that later. But the point is, once again, with modifying the statement will give you different approaches, different angles with the original statement. So that's how you explore things. The unfortunate thing about it is, unlike the negative, you see, we did the negative of the original statement, and we could certainly do the negative of that second version over there in the second line. But also, that conversion to a statement into if-then statement can be done in a different way. So once again, the original statement is every student in this room is an economics major, and then I transformed it into if a student in this room he is an economics major. I could change it into a slightly different version. For example, so once again, if then. Well, I don't really have to make an if then statement. Say it could be simply for any student in this room, he is an economics major. Okay, or if I do want an if-then how about this? Well, let's split the room and the student. So, for the student, now, if he is in this room, because there's one professor in this room, so that makes sense to take a different angle. Then he is an economics major. Okay, so as you can see, if-then statement has changed. So if he's in this room, so the student part has disappeared, and then we're looking at it slightly in a different way. So if I want to take the contrapositive, I would have to. I'm only allowed to reverse the arrow. Okay, that's the contrapositive part, and so then whatever happens to the original part is really not will not allow us to have the same exact statement. So if I try to reverse and say, well, for any student, if he is an economics major, he is in this room. So that still works out. But the hold on a second. No, that's not the contrapositive. That's the converse. The converse remains the same, but let's see. What is the contrapositive of the statement at the bottom?
For student, if he is an economics major, if he is in
No, contrapositive. So not I didn't hear you use not. So you have to use not twice, right? Okay. Yeah. Okay, so as you can see, it is a bit tricky because every statement has different forms, and you can try to take the contrapositive, and then it will. Well, how about what's the contrapositive? Okay, here's the question. What's the contrapositive? What is the converse of the contrapositive?
If it is not in this word, then it is not economic nature.
Are you looking at the top over there? So that's the converse is at the top, and now we take the contrapositive. Say it again.
If he is not in this room, then it is not economic nature.
Right.
Right.
Okay. So okay, let's do the same. Let's as you can see, things are get complicated. But let's go back to even and odd next numbers. Let's see. So once again, if then statement, if number A is even. Okay. So if A is even, B is even, then A plus B is even. Okay, so let's just for practice have the contrapositive of it. So contrapositive. If what?
If A plus B is not even,
Yeah. Oops. Then
would it be both A and B are not even, or one of them is not even?
no, that's a good question. That's a good question. So well, remember the negation. So negation of what? Okay, so then not, let me make it in two steps. And then not, A is even, B is even. Okay, so see, I did negation of, I negated A plus B is even, so it's simply A plus B is not even. Okay, so now I need to negate the first half. A is even, B is even. Well, to make it slightly more explicit, how would put an end there? Okay, so okay, so what is once again the rest of the possible outcomes in the universe other than A is even, B is even?
It would be A is not even, and B is not even.
What's the word in the middle?
Yeah.
No.
Okay, well, it's all of it.
Right. So the negative will be A is not even, or B is not even. Not even. Okay. So that's the negation of same here. Negation of the statement that it has two. So if you look what I have in parentheses, you have two conditions that have to be satisfied simultaneously. That's the and part. Okay, and that's the rule that we're going to use freely, or not freely, but we'll talk about that more and more. How when the two conditions have to be satisfied, the negative will be the negative of the two conditions, but this time connected by the word or. Okay, so yeah.
So in the contrapositive, it's A is not even and B is not even.
No, this is the contrapositive that I have right now. If A and B is not even, they have either A is not even or B is not even. Right. Because if both of them were even, then we would have it. Okay, so as you can see, that is that we negated the statement, which is made of two parts, and we have to be very careful as to use to flip. Not only negate the two statements, A is even became A is not even, and B is even became not even, but also how they're combined together. Okay, so either one or the other has to be satisfied. I think you might remember something very similar. Probably makes sense to stop here and remember something similar in algebra that you did. Remember solving inequalities. Okay, so you see the connection? Well, let's take an example. We'll see soon enough the relation between statements on one hand and numbers on the other, and so that's one way to recognize that connection is right now. So what we are doing is solving inequality. How about x minus 3 lies between 2 and 5. Okay, so it is shortened version. We will. What is the, if I want to expand it to explain what we're trying to accomplish here? So how would I write it out? So this is just too short. So what am I trying to accomplish here with this inequality? Start with x. What do we need from x?
The range?
Well, let me get started. So find all values of x. That's how every equation or equality starts. Find all values of x that satisfy this inequality. Satisfy this double inequality. It is inconvenient, or you can actually solve it with just as is, with this double inequality, but actually makes sense to break it into two. Okay, so one inequality, the other inequality, one, and this is the other. Okay, so let's just write them separately. So 2 less than or equal to x minus 3, x minus 3 less than or equal to 5. Okay, so what's, so in other words, okay, so what's missing? Find all values of x that satisfy what?
Equation.
Say it again?
The top equation.
No, I'm moving to the bottom. So I want to have this sentence finished. There's something missing in this sentence. Find all values of x that satisfy what? Comment there. So what's missing?
Should put an and,
That's right. Why not or?
because it needs both of them.
You need both of them satisfied. So you need a number that simultaneously satisfies the first inequality and the second inequality. So it's very crucial that you put an inequality there at the word and. Okay? Then you solve it. It's really not let's carry it out. It's really elementary things, right? So the first one, x is what is it? Larger than or equal to 5, right? And so I'll carry on this, so keep repeating. So x has to be larger than or equal to 5, and x has to be less than or equal to 8, right? Okay, so now let's before writing the answer, let's illustrate this and separate them. So x larger than or equal to 5, so this is 5, and these are the x's, right? Including 5. Okay? On the other hand, these are less than or equal to 8. Okay? Okay, but I need one answer. So what do I do?
See where they overlap?
What?
See where they overlap?
Yes, overlap, and where there's a better more mathematical word for it. Intersection. So we're talking about the intersection. Okay, so really, if I plug them together, once again, intersection. Why intersection? It is why intersection because of the word in. Okay, so just slide from 5 into the right, and from 8 into the left. Okay, the overlap is right there. This is the overlap section. So this is geometrically, this is the answer. Okay, everything between 5 and 8. However, I want to write it in terms of, so once again, I'm referring to pre-calculus. So this is the operation of taking the intersection of the first ray from 5 to infinity. Does this look familiar? Okay, and then intersection, remember the symbol for the intersection? Okay, the second one is negative infinity 8. And the answer, 8 inclusive. And the answer is 5, 8. Okay, so that is the answer. Obviously, we don't want to talk about algebra as much as this is just an illustration of the logic that we are trying to establish, and how we see a relation between the logic and such words as and or on one hand, and on the other hand, intersections, and intersection corresponds to and what do you think or corresponds to?
Or?
What?
But it's or.
Well, yeah, so if we have or, then what does it correspond to?
Union.
Union. Right. So as an illustration, so once again, imagine that that my inequality was, let's forget about double inequality, let's look at this, these two inequalities, but I put an or here, meaning what? Meaning that, just read it, find all values of x that satisfy this inequality or the other inequality, one of the two. Okay, so, and then you proceed in the same fashion. You still have two inequalities in the same, so I'm solving each of them separately. I end up with, once again, these two rates from 5 to infinity, from negative infinity to 8. But then at the last moment, instead of having or, instead of having and, I have or, and therefore instead of intersection, I have the union instead. So I will have 5 infinity union negative infinity 8. Okay, what does it give me? Oh, real numbers. So as you can see, the choosing one word in the setup of the problem at the top gives me the two very different answers. Okay, so once again, logic and algebra go hand in hand, but really it's not really algebra. What this is more set theory, theory of sets, because it just happens that you were looking at the sets, there were sets of numbers, but we can just these are sets of numbers, real numbers, right? And we took the intersection of those two sets, and then we took the union of those two sets. Okay, but really you can think of each number actually corresponds to a statement of whether or not this number satisfies the first inequality, the second inequality, or both of them, or one of them. Okay, so usually if you want to illustrate that with in a kind of a more a more visual way, this would be the intersection, same thing, same statement A, statement B, and then there's an intersection, A intersection B, or there is a union, A union B. Okay, so are we talking about numbers here? Maybe. Could be numbers, just an example of just above. They could be, however, entities of any nature. That doesn't matter where they are. We can speak of unions and intersections. They could also be the statements that we have made. So this could be. This could be statement A, and this could be statement B. Okay, so then once again, what we illustrate here, X says that, I'm sorry, statement A is X larger than or equal to 5, and Y and X is less than or equal to 8. Okay, so these are the two statements, and then when we combine these two statements, either with the word and, here, and, or the word or here, we will have different answers, right? So here, once again, x greater equal to 5, equal to 8. Okay, so we combine these two statements. So there's some kind of number x, and we have we have two possible statements to be made about it. Whether a statement is true or not depends on x, right? And then we're looking at these statements. We're given x, and then we'll see when their statements are satisfied simultaneously. Simultaneously, or one or the other those. And these are how you can illustrate the truth of the one or the other combination of the statements A and B. So once again, this is, let me make that clear. I'm talking about this, right? The intersection. So you can think of, once again, you can think of these of that we're going to mark there, all the x's that satisfy this inequality, or you can think of it as if it is the statement about x that satisfies both of the inequality on the left and on the right. And on the other hand, here we have the opposite. This is my union, right? It is one or the other is satisfied. So if x is larger than equal to 5 or less than equal to 8, we have good. Okay? So that brings me to, I hope I'm not going too fast. Any questions about this? So once again, wherever you can find some connections to 4 calculus, that certainly you should take it. And so any kind of great only equation inequalities is very much is very helpful in that respect. Another way to look at the same picture is with the so-called truth tables. Truth tables meaning that, once again, depending on x, we either A satisfied or B satisfied or both of them satisfied. One of them. Okay, so then A could be true and B could be or false. Okay, so this is how we do it. We put A here and B. A true false, B true false. There are two possibilities, and there are 4 possible combinations. Okay, so 4 possible combinations of true false for the two statements. And now, however, so these are the two statements. We're forming a new statement. We're forming new statements in two ways. So suppose we start with the statements that have to be satisfied simultaneously, but both of them have to be satisfied simultaneously. Okay, so of course, look at this. The first one over here, both of them are true. Is the whole statement true? Well, yeah, right. So once again, we ask a question about the table is about the intersection. Okay. In the meantime, so the first column is the row at the top is about A, the column is about B. So if I'm looking at this location here, I'm talking about what if both A and B are true, does it mean A intersection B is true? Does it? It does. However, what if one of them is not true?
True.
What?
Still true?
No. They have to both be satisfied. So if one of them fails, then the intersection fails. And if both of them are untrue, then obviously also untrue. Okay. And then we do the same with the union. A union B. So 1. So this is and. Sometimes another notation is this, by the way. Either the set theory notation is the union, logic notation is the hat. Okay. Similarly here, once again, you don't really have to use it. It doesn't save you a lot, and you might forget about that simple idea behind it, which is simply either and or either is satisfied simultaneously, or both of them, or one of them. Okay, so at this point, if both of them are true, then of course the union, we are good, then A or B is true. Just look at the inequality of that intersection at the top. So either it's if both of them are satisfied, then of course one of them is satisfied. Okay. If over here is it true or false? B is true, but B, A is false, but B is true. What about the?
It's true.
It's still true, yes, because one of them is sufficient. Okay, if one of them is satisfied, then that is sufficient. So here, once again, if we flip it, and now this time A is true, B is false, then it's still true. Okay, so and then this finally we have only one untrue when both of the statements are untrue. Okay, so that's all. We combine them, and I guess let's think of illustrations of something that is not algebraic. Let's think of an example of these truth tables where the statements are not about algebra. So I don't know. Okay, say X student is a math major. Let's take a quick look at this, and so that's statement A. Statement B is X is say computer science major. Okay, so then as you can see, then if we are looking at particular students and trying to examine his or her relation to math or computer science major, then we can do it in two ways, right? So either you interested in what is the, if it is and, then what are we talking about? What?
They're both math major and computer science major.
No, they both, it's the same person. It's the same person, it's a double major. So simultaneously math major and computer science major. That's, so in other words, they're double major. Or it does not have any special name, but it's one or the other. So there is nothing, there is no name, unfortunately. But you can see the point that the question is certainly how close person is to this mathematical computer science future or profession. Then you can look at A. You can look at B, or you can look at A and B, which is the most you can imagine. Or if you have one or the other, there are plenty of people which have one. Okay, so all right, so we'll just continue with this and with more algebra now.